Hi guys, I've had some positive feedback on the previous video we did about the process of using figure 4.1 in AS2870 to determine the minimum required slab depth for a particular site parameter. I've also received several emails asking about how to determine the equations of the lines in the log graph 4.1 so that we could use these equations in an Excel program without having to frequently go back to the graph to get the results via the x-axis and y-axis manually. The aim of this topic is how to carry out a linear regression analysis in Excel to justify the equations of the lines in figure 4.1, which in this case, you have HS less than 3 and the HS greater or equal to 3. Regression analysis is actually a great tool, especially for engineers and data analysts in general. Many times as engineers, we want to develop a relationship between two variables from a number of data points, for which then we can determine a set of equations which represents this data. The way to do this is via regression analysis. So say, for example, we want to develop a relationship between the movement ratio and maybe the number of cracks in a particular home. Or some people want to develop maybe a relationship between the differential deflection and the crack width. We can actually gather these data points together, and through regression analysis we can then determine the best fit graph to represent the data. For this reason, the code committee took the log of this graph in figure 4.1 because that was the best fit line to represent the data. I think many of us were wondering, why did they take the log of the stiffness? Well, because they wanted to determine a linear line which fits the data at a perfect level. So we will talk a little bit about this in further slides. If we are not using Excel, then we probably have to do this calculation manually, and this will take forever. I mean, forever and ever. So to do it manually, we then have to obtain a series of equations such as the value of Pearson's correlation coefficient, R. You might need to go back to probably year 12 maths, where R has a formula, a hectic formula, and that's sort of the sum of xi, which is the values of the x variable, minus the x bar, which means there is the mean value, and then there's yi, the values of the y variables, and then the y bar. So it is a big formula, and ultimately what we need to find is something called the coefficient of determination. So R squared is a coefficient of determination. R squared basically is how well a statistical model predicts the outcome. So why is R squared important? Because it shows us the correlation between 2 points on a graph, whether it could be positive correlation or it could be a negative correlation, and sometimes there are no correlation at all. In a nutshell, the closer R squared is to unity, then we know that the graph is better fit through the scattered points or through the data points that we have put in. So the closer R squared is to 100% or to unity, then we know we have a better fit. In this case, we need to carry out a linear regression analysis because the line in figure 4.1 represents linear log regression. In general though, from a scattered plot, we could use many regression analyses to find the best fit to the graph, such as lin, log, simple linear, polynomial, exponential, and the list goes on and on. So let us now go to the Excel file, and I will show you the quickest way to do this. Here we have figure 4.1, and in table 1 below, we have x coordinates with the corresponding y coordinates. I chose this example with the first line where hs is less than 3, and maybe you can give it a shot on the second line yourself and see how you go. There are two methods that we can use here in Excel to determine the linear regression equation and the coefficient of determination R-squared. The first method is the easy method, and that's only if you just want to determine R-squared and the regression equation. With the second method would include more statistical data if you need much more refined data. I'll explain both methods quickly. In step 1 of the first method, what we need to do is determine as many x and y coordinates for the line that you choose to do the equation for. So in this case, we have the linear log line, which has been already drawn for us in figure 4.1. So what I've done, I went up to the x-axis and I went one by one. So at point 8, I found out the equivalent y value, which is 0.6, and then at 8.5 is approximately 1.7. At 9, I got about 2.65. 9.5, so I've got about 3.7, and at 10, I got about 4.75. Okay. The second step is highlight the table. You can include the title if you want. You don't have to, but just highlight the table. Then go to Insert. Then click on the scattered graph diagram. You see a selective diagrams here. I am using 2007, a bit of an older version of Excel, but it's very similar if you're using 2013 or later versions as well. Make sure you make the graph a little bit larger so that you can see the scattered points clearly. Okay, then click on the actual graph itself. Once you set the graph, click on the actual graph itself. Look up on the top here and see that little graph with a line and function on it. Okay, just scroll down and see the graph with the function f of x on it. Click on that function graph and check it out. And here we go. Abracadabra. We have the regression equation of y is equal to 2.06x minus 15.86. And you can see that the line is perfectly fit through the points. And what's even better is R-squared, the coefficient of determination, was 0.999, and that is literally flawless. It means that there's a very strong correlation between the points, and this equation is amazing. Okay, R-squared of 0.99 means that we have a really good strong correlation between the coordinates that we have chosen. Okay, so keep that equation in mind. Y is equal to 2.06x minus 15.86. I will quickly go through the second method for a better and more statistical information of the graph. Alright, you can see in this little diagram y bar is equal to alpha plus beta times x, and that's the linear regression equation. R-squared again is a coefficient of determination. Alpha, intercept alpha, the slope beta, regression equation, all of that, the Excel will determine it for us now in the second step. You can also determine the standard error of alpha and beta, the p-value for alpha and beta for hypothesis testings as well, and the CI, which is a confidence interval of alpha and beta. So there's more information in this. Okay, so how do we do that? Well, step 1 in the second method, click on the data, both the x and y coordinates, click on the entire data. And then step 2, go and click on Data Analysis. Step 3, scroll down and look for regression and click on it. Okay? That's what we want to do with regression analysis. Step 4, input the Y range and then input the X range including the title. And if you have included the titles, click on labels. Okay? Step 5, enter a name for the location of the output results in a new worksheet. In this case, we will call the new worksheet regression. So all the results will actually automatically be inputted in the new worksheet. So we just type regression and then press OK. Here we go. You could see the new worksheet called regression with the full data analysis, which includes the regression equation with the intercept alpha being minus 15.86 and the slope beta is 2.06, and we can also see the other data as well, such as the standard error for alpha and beta, as well as the p-value for the hypothesis testings. And this is a great tool for engineers. That I believe every engineer should know this. So it's a great estimating tool for data analysis. All right, we're almost there. So let's go to the analysis tab. Now from memory, we can always remember the equation that we found is y is equal to 2.06, which is the slope, times x minus 15.86. Okay, this is for hs less than 3. Therefore, we can rearrange, resubstitute. We can say x is equal to 0.485y plus 7.67. So what did I do here? I just took out x by itself. So I put 15.86 the other way and then divided everything by 2.06. Okay? Now remember, y on the vertical axis is ys divided by delta, which is a movement ratio. So let's rewrite this equation again. We can say x is equal to 0.485 ys divided by delta plus 7.67. Right? I'm going to call this equation 1. If you remember actually in the previous video, we had for the long direction, we had ys divided by delta, which is 1.99. And you can see here, I've got it here in this graph on the right here, at 1.99, the approximate value for x was 8.6. Okay, that's what we assumed in the previous video. But let's see from the equation that we have found out from equation 1, if we substitute ys over delta in that equation 1, we get x is equal to 8.64. So it's virtually the same. It's almost the same. So this is a great result. Therefore, we can conclude that the equation 1 is fantastic and satisfactory. It will make our life so much easier, especially in design, where we want to use an Excel program to work out the depth of the slab without the need to go back and manually look up the graph 4.1 every time we want to work out the depth of the slab. So I hope this regression analysis was interesting and fun. And yeah, and if you thank you so much for watching again. And if you have any questions or any comments, please do not hesitate to email me. Thank you again, and I look forward for our next topic. Thank you.